their types and categories based on technology. So we came up with active and passive. Again, analog, digital. So in this small tree that we have covered, all of this means analog. Active filter, passive filter, analog filter, all of these are different types of analog filter. In the same sequence you have seen in the lab as well. We have Butterworth, Chebyshev 1 and 2, elliptic, ripple, etc. A line of filters that have been worked on by people for quite some time. Then the pure digital domain, which is here, we have two types, IIR and FIR, infinite impulse response and finite impulse response. The IIR is actually a conversion of these analog filters into digital form only. But FIR filters are pure digital filters that were developed by using digital signal processing from the beginning. Then we went through the structure of these two, because direct form 1, direct form 2, cascade and parallel. So 4 types of structures were studied. I'll show you the pictures once again just for refresher. In case of FIR, we have studied so far only one, which is tapped delay line, or TDL as it's called in short. And the second one we will want to look at is the cascade structure. That will basically complete our discussion on how do we actually design a filter. We use some tools to do this. So that's what I would like to do today. Going back to the filter slides. So all of this is about analog filter, and I told you in the beginning I'm just covering this as a background that you should have for the digital filter. The digital filter discussion started from this point, where we know that the filter will work only on binary data and will produce only binary data. For the real world, this binary data and output has to be converted into digital form, into analog form, before it can be used in the real world. Similarly, real world signal has to be converted to digital before it can be given to the digital filter. So this is trivial. Then we went through some of the properties, and then based on those properties we came up with the equation, the ARMA equation as it's called, this one. And then we jumped into the types of filters, IIR, FIR, and somehow we found out that the IIR filter essentially is a physical implementation of the ARMA equation. This is the transfer function for IIR filter. We derive ARMA equation from this, and that gave us the direct form first, in which xn is multiplied by different coefficients and delayed, different coefficients, delayed coefficients, etc. And the second term is also similarly done. Output y delayed element multiplied by a1 delayed element, and then we combine them into what is called the direct form 1. But then since this is addition, x plus y is equal to y plus x, doesn't matter. So using this constant, their positions were changed and the number of delay elements were reduced. This became the direct form 2. Now out of the direct form 2, if we just look at the first part, I call the window structure, that became our bichord structure, for which we started talking about this bichord basic structure, which was converted into different forms of first and second order subsets. The parallel form was obtained by taking the partial fraction. What happened?
Yeah, she's coming back.
Okay, hopefully. Yeah. So then we started the FIR structure. That's where we were yesterday. The last class. Direct one, or a TDL, it's called the tapped delay line, as we discussed last time. You take the equation and you just apply implementing it in this form. Okay, let's take an example of that. Suppose my filter, so my output y of n is equal to, let's say, y of n minus 1. You can see it. Write down. Plus 0.5 y of n minus 2 minus 0.1 y of n minus 3 plus 0.1 y of n minus 4 minus 0.2 y of n minus 5. Suppose this I just made up the filter like that. So my output value will depend upon previous 5 values, 1, 2, 3, 4, 5 values. Okay. So the tapped delay line structure is you start with the initial value. So instead of calling this as y, we know that this is how it goes. You enter a signal came out filtered. Essentially, it's the same signal that goes in and comes out. It's just changed a little bit. That's why I wrote y. To understand mathematically, it's better to consider this as a different signal and this as a different signal. So we're saying that a different signal came into the filter and a new signal came out of the filter. Although it's still the same signal, just few properties have been modified. So easily I can say this is x, this is x, this is x, this is x, and this is x. Now here, when we start doing the x here, that means, okay, if I have y of n, it should have some influence of x of n as well. We don't have x of n in the equation, because we started our equation with y, not with x. Safe to say that we can have another term added here, x of n plus this whole thing. Now everything that is governed here is through the coefficients. What is here, what is here, what is here, what is here, what is here. That is the main thing that defines our filter. I can say that my filter is this. At n equal to 0, it's 1. This first term. xn has a coefficient of 1. xn minus 1 also has a coefficient of 1. xn minus 2 has a coefficient of half. xn minus 3 has a coefficient of minus 1. Minus 0.1, sorry. Minus 0.1, so 0.5, so it is. And then plus 0.5, or plus 0.1, over here. And then minus 0.2, so double of that will be here, approximately. So this structure now represents my filters. These coefficients are my filters, and this is what I can use to, I can use it as a matrix, as a vector, and then I just use it with my filter. Now, how can I apply it with my signal? Sorry, how can I apply it in any signal? How can I apply this on any signal?
Shouldn't it be the opposite?
Why?
Because we have n minus 5, so delayed 5.
Yeah, you're right. But when we look at the application of this, what will happen? I was about to mention that anyway. So you have a signal X, you want to apply this filter H on it. This is my filter H. My signal X is coming. What is the function in between? What is the operation? Convolution. Okay. So what is the first step of convolution?
Third step.
First step of convolution. So it will become the same. So that's why we keep it like that. When we apply it on the real signal, it's actually the other way around. So first step in convolution, you flip the signal, and then you start shifting it, multiply and add, multiply. Okay. All right. So that's this. Okay. Now, how do I represent it in a structure? X of n. The coefficient of x of n goes in here with 1. Add in it x of n minus 1. How do we produce x of n minus 1? So this will be our main structure, like a step, always. Tap delay line is like a step structure, repeated one after the other. That's why I'm using different colors. Another step here. This one is z minus 1. Z to the minus 1. And this will be your second coefficient. In this case, is also 1. Third, this one. Starts with a delay, goes down with a step like this. Z minus 1. This will produce x n minus 1, n minus 2. X of n minus 2 has a coefficient of 0.5. So we'll write down 0.5. Next, n minus 3, one more step, z to the minus 1, the n minus 3 is minus 0.1. Next one, let's bring the red color again, n minus 4, so z minus 1 plus 0.1, and the last one minus 0.2, so z minus 1 minus 0.2. So bipod was, remember the window, this is the steps. If you have difficulty remembering it, just remember that each term you start with xn, the ending result, which is here, is your volume. So start with this. First sample comes in, you perform this multiplication, then all the way in the output. That's for the only first sample. The second sample comes in, which is the delayed one version, multiplied by 1, added with the previous one, this one, and so on. So actually the correct result of y of n will appear only when you have 1, 2, 3, 4, 5, 6 input samples available. So the more the length of the filter, the longer the filter, the more samples are needed first to make it possible that this filter can filter. But this is the general structure. Again, if you cannot remember, so it's just a step structure. First time, this is your first coefficient, x0. Second time, another step. This will be z to the minus 1, this will be h1. Next step, same type of step, z minus 1, h2, and so on. So this filter can be increased like this as much as you want. And that's why in terms of real hardware, tap delay lines are available, especially in communication circuits. They use lots of tap delay lines for compensating the delays, adding the delays, filtering the signals especially coming from satellite. When the signal starts from satellite, it takes a very long time for it to reach because it has to go through a lot of distance and has to go through lots of layers, atmospheric layers. And some of the layers are very, very dangerous, by the way. They are called. This is called the ionosphere. The ionosphere is where really charged particles are there. When the electromagnetic signal goes through charged particle, its characteristic can also change. So they have to perform filtering to recover that signal back. So this was direct form. There is another form called the cascade, which is exactly the same idea as in case of IAR, except that what we do, instead of writing the whole polynomial in one shape, we break it down into second order roots. Instead of having a long summation n equal to 0 to m minus 1, h0 z minus 1, h0 plus h1 z minus 1, h2 z minus 2, we can break it down into roots. So b0, b1 z minus 1, b2 z minus 2. That's one root. Second root multiplied by this, third root multiplied by this. You can multiply them in the structure, in the factors of 2, power of 2. The benefit of that is that now you can implement each root separately, each root separately, each root separately. If you look at this root, it is half of your window, the one that we saw earlier, going down on the side, going down. Half of your window that we saw in IIR. This speeds up the process only. It gives you a better result even with the first factors sample. It needs 2 samples, for example. Okay? Even with 2 samples, you are getting a better result as opposed to this structure even after 2 samples. So this one is a bit more delayed in it because it has to wait for every sample to come. Here, the effect becomes more prominent when only the first chord, bichord is available. The first root is available, you start getting a better result in the output. But still, the concept is the same. Irrespective of the structure, how do we design this filter? So for that, let me take you to MATLAB. Now, if you have MATLAB available with you, you can try this as well with me. We would like to start with, first of all, generating a noisy signal, the way we did in no words and the dam, etc., etc. So, we don't even have half of the class. Okay. We need to finalize the dates for exam. Anyway, we'll see. So, I was doing this some time ago, so okay, let's see if I have FS. So we started with a sampling frequency of, let's say, 1000 samples per second. The purpose of doing that was, if I want to see the actual frequencies in the spectrum, I can refer to these values. We have already seen how it's done. Almost nobody did it in the exam, so that's fine, because you'll be able to see exact frequencies only when you follow that procedure that I went through in the class. In case of Fourier transform, Fourier series, how do you actually develop the frequency vector, multiply them, but etc. Anyway. So I started with a sampling frequency of 1000 Hertz, which means my sampling time is 1 over 1000, which is 1 millisecond. Okay. Then I'll define, let's say, length of my total measurement. I'll say the same as sampling time, sampling period total. So 1000 samples. I want to come up with, you remember in the exam there was a condition that you have to develop a time vector from 0 to 999. This is how you do that. So within that range of 0 to 99, so TS will be modified, but 0 to maximum length minus 1 times the time will give you a time vector from 0 to that last sampling time that you have. Okay. Now we want to define a signal X. So the way I have defined it is here. Let me do this part first. Okay. So I'm combining a sine wave and a cosine wave, weighted cosine wave, or 2 different frequencies. The sine wave has a frequency of 10 Hertz, 2 pi ft. Cosine has 2 pi f, 100 Hertz frequency. Is our sampling frequency okay for this signal? Or will we have problems?
Yes.
Highest frequency is 100 Hz.
Yes.
Sampling frequency is 10 times of that, which is 1000, so we are okay. Sine or cosine should not confuse you, not a problem. So this will generate a compound signal for us. How does it look like? We can check it with plot. T comma X. It looks strangely like this. I can just use a smaller window to see these curves. Okay. So actually the 10 Hertz frequency is the sine wave like that. On top of it is these multiple variations of 100 Hertz frequency. Okay. Next, I want to make it noisier.
Then
So we did that xn thing. X plus rand n. What type of noise is that? Rand n. What does that mean? N represents normal. Normal is Gaussian. Gaussian noise is from -1 to +1. Between this range, any value of randomly selected numbers will be added to x. Before adding, it's multiplied by 0.2. So the magnitude is really reduced. The noise is not very strong.